long. So this budding hybrid ABM model, SD-ABM model, this is going to show a very different sort of hybrid modeling than what we just saw. What we just saw is each individual has within them some discrete dynamics captured with state charts and some continuous dynamics captured with stocks and flows. Okay? Very useful notion. Describing continuous dynamics, the regulatory processes that are operating using stocks and flows, which are an exquisite language for describing those sort of features. Ladies and gentlemen, this model, this budding hybrid model, shows something very different. Here, we are going to use a compartmental model for most of the population. The population, for example, of normal glycemics will be characterized using a stock and flow model. Once individuals reach a certain point in their risk continuum, they will be turned into agents. And then, from thence forward, they will proceed as agents. And by virtue of having agenthood, by virtue of being individuated as individuals, we can characterize many we could secure many virtues. Let me enumerate some. We can put them into a GIS context. We can put them into a network context. We can capture their history over time. We can capture their family context. We can examine the impacts of targeted interventions that are based on their history or their particular aspects of heterogeneity. We can simulate their encounters with the care system. We can and record histories of those episodes of care. There's many virtues that we get through an individuated representation. I've just listed some. But we don't have to secure the benefits, mark my words, to secure the benefits of an individual representation, we don't have to use that representation for the entire model. We can have part of the model, populations of less focal interest, in an aggregated compartmental fashion. And then once they reach a critical point, we turn them into agents. Okay? Another example would have been, for example, do you remember that just in this room, not an hour ago, we were looking at a model where we had implementation science dynamics. We had trained the trainers, remember that? And then those trainers trained peer educators. And then when peer educators reached full level of their training, then they could go interact with people in the population and encourage smoking cessation among older individuals or whatever. We really didn't need those peer educators all through their training to be represented as people. But once they reach their graduation, then maybe they become people and they're represented as people in the population. Lots of virtues for having compartmental modeling for most of the system, individual-based model for part. So this shows this in a most simple form. And in a lot of my boot camps, I build this. This takes about less than an hour to build. Here we have non-diabetics, and non-diabetics live in this stock. This counts the number of people, and they have a mean time to develop diabetes. And so we have a stock and flow, and the flow is non-diabetics divided by mean time to develop diabetes. Okay, that's how many people flow down here. This is just classic compartmental modeling. And then when they flow into the state, ladies and gentlemen, they get created as agents. How does that happen? Well, there's this event that goes off when there's somebody waiting to be created as an agent. When there's more than one person waiting to be created as an agent, it will create them as an agent. It will go and add them to the population. That's exactly what this does. It adds them to the population. Loops through and adds each of these people to the population. So let's run this thing. Ready? Watch this. We're going to run it. Boom. Here we go. Here are these diabetics, and they are becoming agents. And as agents, now we can simulate them going forward in whatever ways. Now, one of the models we worked on like this 2 years ago at a boot camp, 2.5 years ago, 1.5 years ago at a boot camp, actually people became agents for a certain amount of time, then they stopped being agents. So they were agents for a certain point in their health continuum, and then they stopped being agents at another point, and they flowed back into stocks. So the point here is we can use much of the model, we can have much of the model in stocks and flows, and then just pieces of the model as agents. Now, there's no silver bullet here. There's going to be limited resolution when you have an agent circulating, and they need to infect non-agents. There's some random mixing again, because the ones who are still just in compartments, we can't distinguish them as individuals. But we can have individual interactions. So if people maybe become agents when they reach the high risk stage, and then when they've entered into the at-risk population, they maintain as agents. Maybe a lot of the interactions are among people at that stage. A model like this can run really fast if a lot of the population is not agents, but it can secure a lot of the benefits of agents for other pieces of it. So that's another example of a hybrid model where we have kind of lateral relationship between, on the one hand, stocks and flows, and on the other hand, agents. Okay? Another version of hybrid models. We've seen several of them this morning. Even the model with basic health economics was a hybrid model. Okay, now the final model I want to look at